and welcome to Meduhub. I am Neha Gupta, a part of her chemistry faculty, and today we are going to discuss about alkynes. Alkynes are hydrocarbons which contain a triple bond. The simplest of the alkyne would then be containing two carbons with a triple bond in between them, and to satisfy the tetravalency of carbon, we'll add a hydrogen. Alkynes are also called acetylenes, and the general formula of alkynes is CH2N minus 2. Now, what is the structure of alkynes? We have a carbon here with a triple bond. There's a hydrogen here. Each of these carbons is sp hybridized. Okay. So, the sp orbital of this carbon forms a head-on sigma bond with the sp orbital of this carbon here. The remaining two bonds are pi bonds. So between these two carbons, there is one sigma bond which is formed by head-on overlap, and there are two pi bonds between these two carbons which are formed by sideways overlap of the p orbitals of carbon. Now these two remaining bonds here with the hydrogen are again sigma bonds which are formed by head-on overlap of the 1s orbital of hydrogen with the other sp orbital of this carbon, and here the other sp orbital of this carbon with the 1s orbital of this hydrogen. So in totality there are 3 sigma bonds and 2 pi bonds, and between the two carbons there are 2 pi bonds which are formed by partial overlap and 1 sigma bond which is formed by a head-on overlap. So because of this, what do you see? If we talk about the bond strength, if we have a triply bonded carbon and have a doubly bonded carbon and a carbon which is singly bonded with another carbon, the bond strength would be maximum here, and it will reduce as you move on from alkynes to alkenes to alkanes. And if we talk about the bond length, again comparing these three, alkynes, alkenes and alkenes. Here the bond length would be the shortest in alkynes, the least, and they will be the most in alkanes. So this is the order for bond strength, and the reverse order is followed for the bond length. So we have talked about alkynes and their structure. Let us look at their nomenclature. So for the nomenclature, the prefix will depend on the number of carbon atoms. That is always the case. And the suffix here will be -ines. So if we talk about the simplest of the alkyne, it has 2 carbon atoms, 1 hydrogen, a triple bond here. Since there are 2 carbon atoms, it is the prefix is eth and suffix will be -ine, so it is an ethyne. Ethyne is also called acetylene. It is one of the most important alkyne, acetylene. And in the simple system of nomenclature, like the common system of nomenclature, this compound here with 3 carbons can also be called a methyl derivative of acetylene. So we can call it methyl acetylene. But according to the IUPAC nomenclature, what do? We find the longest carbon chain and number it 1, 2, 3. 3 carbons, so it's a propyne, but the triple bond is at the first carbon, so prop-1-ine or a propyne. Look at this one. This is a little more complicated. Here we have the longest carbon chain is 1, 2, 3, 4, 5. The longest carbon chain contains 5 carbons. From where will we start the numbering, left or right? Let us start numbering from here first. 1, 2, 3, 4, 5. The triply bonded carbon is getting the number 3. If we start from this side, 1, 2, 3, 4, 5. So if we start from this side, the triply bonded carbon is getting the number 2. According to the lowest locant rule, we will start from here. So we'll number it. So it's at 4th carbon, there is a methyl group here. So we have 4 methyl pentyne. And where is the triple bond? It is at the second carbon, pent 2 hydrogen. Right? Now look at this compound. This contains a double as well as a triple bond. 1, 2, 3, 4, 5. 5 carbons in a straight chain. The double bond is here, the triple bond is here. Now if we start numbering from this side, 1, 2, 3, 4, 5. So the double bond and triple bond are getting the number 1 and 3. If we start numbering from this side, 1, 2, 3, 4. 2 and 4. Again, according to the lowest locant rule, this will be favored and we will start numbering from here. This is 1, 2, 3, 4, 5. This will be pent 1 in 3 ion. Pent 1 is 3 ion. Now, we have spoken about univalent groups. So you remember in alkanes, if we remove a hydrogen from methane, for example, if we remove a hydrogen, we'll get a CH3 group which is called a methyl group. That is an alkyl group. Similarly, in alkynes also, we can get univalent groups which are called, which will have the suffix -ine. Alkynyl. So an alkynyl plus hydrogen will give us an alkyne. Take this example. The parent alkyne of this one will be an ethyl molecule CH. But if we remove a hydrogen, we will get this group which will be called an ethynyl group. Right? Here, the parent hydrocarbon here is propyl, but we have removed the hydrogen from here. So this is propynyl. This is similar to this, but the position of the triple bond is varying. So we'll number it 1, 2, 3. So this will be a prop 2 inyl. Right? So these are the univalent groups which are derived from alkynes. We have spoken about structure and nomenclature. Let us see what isomerism is exhibited by alkynes. Isomerism. Alkynes show structural isomerism. In structural isomerism, the molecular formula of the compounds is the same. What differs is how the carbon atoms are arranged in the molecule. The arrangement of the atoms differs. So there are two types of structural isomerisms. One is position, one is change. Let us take one simple example of a butane. C4H2N-2. 4 to the 8 minus 2 is 6. So for butane molecule, we can draw two structures. 4 carbons in a chain. The triple bond is here. CH2, CH3. Or we can draw another structure. 4 carbons. Triple bond is not between the first and the second carbon. Triple bond is here. CH3, CH3. This is called but 1-ine and this one is called but 2-ine. Now can you see what isomerism is exhibited? Here only the position of the functional group, which is the triple bond, is varying. Here the functional group is at the first carbon, between the first and the second carbon. Here the functional group is between the second and the third carbon. So this is called position isomerism. Position isomerism. If we take another example of, say, pentine. Pentine will be C5H8. So we can draw three structures for pentine. 1, 2, 3, 4, 5 carbons here. First, the triple bond is here. H, CH2, CH2, CH3. In the next, the triple bond can be here. 3, 4, 5. Triple bond is here. We draw CH3 here. Satisfied. satisfied, CH2, CH3. Or there can be branching. 4, CH3, and the triple bond is here. CH, 1, 2, 3, 4, H here, and CH3 here. How will you name these according to the IUPAC nomenclature? This will be pent 1 ine. This will be pent 2 ine. And this will be 1, 2, 3, 4, 3 methyl pent 1 ine. Now, if you look at these two here, both are straight chain alkynes. Only the position of the triple bond is different. Here, the triple bond is between the first two carbons. Here, the triple bond is between the second and the third carbon. So, these two are showing us position isomers. Position isomerism. These two are position isomers. Now, if we talk about this and this, here the basic carbon skeleton is changing. This is a straight chain carbon skeleton. There are 5 carbons in a straight chain. Here we have 4 carbons in a straight chain and there is branching at the third carbon. So, this one is called a chain isomer. Similarly, the first and the last one also, these two are also called chain isomers. Because this is a straight chain, this is a branch chain, the number of carbon atoms is the same, the molecular formula is same, the basic carbon skeleton is different. That is why these two are called chain isomers, right? Now let us talk about the physical properties of alkynes. Physical properties. So if we look at the first 3 members containing 2 carbons, 3 carbons and 4 carbons, they are gases. From C4 to C12 are liquids. C5 to C12 are liquids. And C13 onwards all are solids. They are colorless, odorless. Though the first member, that is ethine, it has an ethereal smell. Rest of them are colorless and odorless. Now, as the molecular mass increases, their boiling point, melting point, viscosity, density, all increases with increase in the molecular mass. These are slightly polar, very weakly polar, but they are insoluble in water. Insoluble in water. Though they are soluble in organic solvents like benzene, ether, etc. Right? Now we have to talk about the acidic character, which is very important. Why is it that alkynes are acidic in nature? So there are a few reactions which are observed in the case of alkynes. Acidic nature of alkynes. So it is seen that ethine reacts with sodium to form sodium ethynide and gives H2 gas. Similarly, now this monosodium ethynide reacts with another molecule of sodium to give a disodium ethynide plus half H2. Alkynes also react with NaNH2 to give again sodium ethionide and ammonia. Now these are the reactions which are not observed in the cases of alkanes and alkenes. Sodium and NaNH2 sodamide are strong bases. Now alkynes react with strong bases to form a salt and release hydrogen. These reactions are not given by alkanes and alkenes. This means that alkanes and alkenes are not acidic, but alkynes are acidic. This can be used to distinguish between alkanes, alkenes and alkynes. Why is it that this proton here, this hydrogen here in alkynes can be so easily displaced by sodium? What is the reason that this hydrogen is acidic in nature? So that can be seen very clearly from the structure of alkynes. Now in alkynes, in triply bonded, the carbon is sp hybridized, whereas in alkenes, it is sp2 hybridized. In alkenes, it is sp3 hybridized. Now the S character here is 50%. Here it is 33.3%. Here it is 25%. The S character is the maximum in alkynes, and because the S character increases, the ability of the nucleus to pull the electrons towards itself increases. Electrons are pulled with more force, and because that increases, that means the electronegativity of this carbon increases. Electronegativity increases. So because the S character is the maximum in alkynes, the electronegativity of this carbon is the maximum, and it can pull the shared pair of electrons more towards itself, which makes the release of the proton. Let's take this case, which makes the release of this proton much easier because the electron density between these two, this carbon and this hydrogen, is pulled more strongly towards this carbon because of its sp nature. This hydrogen can be released as a proton, and this is the reason that alkynes behave as acids. They are weak acids, but alkanes and alkenes are not acidic in nature. This is the difference between the three types of hydrocarbons that we have studied. Now, if we take the case of, if we talk about acidic nature, we can say that acidic nature follows this order. And if we take an ethyne, a propyne and a butyne, what will be the order for acidity in these three compounds? Here we have two hydrogens which can be released as protons. Here in this alkyne we have only one hydrogen which can be released as a proton. This other carbon, which is triply bonded, is not bonded to a hydrogen. In this case, these triply bonded carbons are not bonded to any hydrogen. So the acidity is the maximum here, it's less here, and this is not acidic. So this one, this is butyne. This isomer of butyne will not give this reaction with sodium or sodamide, right? Next important topic is the preparation. There are two methods by which alkynes can be prepared. The first method is from calcium carbide. So ethyne is the most important of alkynes, and it can be prepared from calcium carbide. From calcium carbide. Now calcium carbide is produced by, first we heat limestone. On heating limestone, we get quicklime, CaO and CO2. Now this quicklime here is treated with coke. What is coke? It is a hardened grey material which is made from coal. It is a fuel, but it has very less impurities, and it is made by heating coal in very less quantity of air. That is why it is almost pure carbon and very less impurities. When you heat quicklime with coke here, we get calcium carbide and carbon monoxide. This calcium carbide, when treated with water, gives us ethyne and calcium hydroxide. So this reaction is a very important reaction for the preparation of an ethyne using calcium carbide. There is another way to prepare alkynes, which is from vicinal dihalides. Vicinal dihalides. Vicinal dihalides are alkenes, are haloalkanes in which the halogen atoms are present on adjacent carbon. So let's take the simplest one. Br, Br, H, H, H and H. This is dibromoethane. This is a vicinal dihalide when it is treated with alcoholic KOH. A molecule of KBr is ejected, water is ejected, and we get dehydrohalogenation takes place. Dehydrohalogenation from this molecule takes place. So let's say this hydrogen and this bromine is removed and we will get CH, Br, double bond C, H and H. This is a bromoalkene. Now when this bromoalkene is treated with soda amide, NaNH2, ammonia will be released, NaBr will be released and we will get the corresponding alkyne. CH triple bond CH. We will get ethyne from dibromoethane. So what do? We treat it with alcoholic KOH followed by treatment with soda amide. Let us take one more example. We have CH3, C triple bond CH. This is propine. If we treat it first with alcoholic KOH, second with soda amide, what will we get? We will get a dibromo. Dibromopropane, and we will treat it with alcoholic KOH and NaNH2. What will we get? First, dehydrohalogenation will take place and then again dehydrohalogenation will take place. Both these bromine atoms and hydrogen atoms will come out and we will get the corresponding alkyne. So this is the method for preparing alkynes from vicinal dihalides. There are two methods now. One from calcium carbide. Calcium carbide method is used for the preparation of ethyne, and other alkynes can be prepared from vicinal dihalides by treating with alcoholic KOH and soda amide. The next and the last topic for alkynes is the chemical reactions of alkynes. The first reaction is reaction with sodium and NaNH2. We have already studied this under acidity of alkyne. So when an alkyne reacts with sodium or NaNH2, which are strong bases, either hydrogen or ammonia is released and we get a salt. This tells us that alkynes are acidic in nature. Now next is electrophilic addition reactions. Electrophilic addition reactions. Electrophiles are species which are electron deficient. Hence, they seek substrates which are rich in electron density. Because alkynes have a triple bond, which means there is a lot of electron density between these carbons, electrophilic addition reactions takes place with alkynes. So what happens? Let's say we have H, X here, positive, negative. In the first step, this gets added on and we get a carbon cation. So, This vinylic carbocation then gets attacked by the X minus here to give us X, this product. The first reaction that we have to study here is addition of hydrogen. Addition of H2. This is also a reduction reaction which you have studied earlier. So if you have an alkyne and hydrogen is added to it in the presence of catalysts like nickel, palladium or platinum, finely divided nickel, palladium or platinum, first we will get an alkene and then further addition of hydrogen will give us an alkene. So the process is from alkynes, when adding hydrogen, we will first get alkenes and then further we will get alkenes. If we have a propyne, we add hydrogen to it in the presence of say nickel. Finally, we will get a propane as the product. And before that, we will get a propene. Further adding hydrogen, we will get a propane. So this is the addition of hydrogen which gives alkenes and then alkenes. Next is addition of halogens like chlorine or bromine. When chlorine or bromine are added, we get a dihaloalkene and then further addition of another molecule of chlorine or bromine gives tetrahaloalkane. Let us see. We have ethyne. We add bromine to it. First, we will get this H. Dihaloalkene and further addition of bromine will give us tetrabromo derivative BrBrH. So what is happening here? Bromine is getting added on to ethyne and this is a very important reaction for test of unsaturation. This is just like alkenes. Since bromine is getting added onto the unsaturated bond between these two carbons, the reddish brown color of bromine is discharged. This reaction is used for the test of unsaturation. We can see in a similar manner, chlorine also gets added. So if we have propyne and add chlorine to it, first we will get and then we will and further addition of chlorine will give us a tetrachloro derivative CnH. This is addition of halogens. The third reaction is addition of hydrogen halides like HI, HBr or HCl. When hydrogen halides are added onto alkynes, what we get is geminal dihalides. Geminal dihalides are dihalides in which the halogen atoms are attached to the same carbon. In vicinal, they are attached to adjacent carbons, but in geminal, they are attached to the same carbon. So, on addition of a hydrogen halide, we get geminal dihalides. This is again a Markovnikov's addition. Third, addition of HBr, HCl, HI. If we have ethyne and HBr gets added onto it. The final product that we will get is this. It is dibromo 1,1 dibromo ethene with geminal dihalide. Now, why do we get geminal dihalides? Let us look at the mechanism. The mechanism is a carbocation formation mechanism. So, in the first step, we have HBr. This hydrogen gets added onto here to give us this bond moves here. And here double bond CH2. Here now bromine will add on Br minus. Okay, this Br minus will attack here to give us CHBr double bond CH2. Now in this molecule, a further addition of bromine, let me write it down here. Now another molecule of HBr will add on to this. So here two molecules of HBr add on to give a geminal dihalide product. Again, this hydrogen can either attack this carbon or this carbon. Let us see what will happen. The two cases, if this hydrogen attacks either this carbon or this carbon. If it attacks this carbon, we will have this carbocation here. Or if it attacks the other carbon, we will have this. This is the first one. This is the second one. Now this carbocation will be more stable. Why? Third reaction in electrophilic addition reactions that you have to study is addition of HBr, HCl or HI. For addition of hydrogen halide. This is an electrophilic addition reaction which follows Markovnikov addition rule. It is a Markovnikov addition. It follows a carbocation formula, and the product is a geminal dihalide. A geminal dihalide is a haloalkane where the halogen atoms are attached to the same carbon atom. In vicinal dihalides, the halogen atoms are attached to adjacent carbon atoms, but in gem halides, the halogen atoms are attached to the same carbon atom. Let us see an example. We have ethyl. It will add on two molecules of HBr. First, it will give us this. And it will add on another molecule of HBr to give us the geminal dihalide. Br here. So bromine atoms are attached to this carbon. So it is a geminal dihalide, or we can call it 1,1 dibromo ethane. Similarly, if we have propane, triple bond CH, it adds on HBr. Markovnikov's rule is followed, and the negative part of the addendum goes to the carbon atom having less number of hydrogen. So this Br will get added on to the middle carbon here. So we will get CH3 C BrCH2, and then it will add on a further molecule of HBr. Again, this Br will get added on here only. We will get a geminal dihalide product here, CH3. So this is the product. Now we have to see why this is happening. For that, we need to look at the mechanism. So we have a propine. In the first step, there is protonation of this propine. CH3. See, hydrogen can add on here or here. If it adds on here, we get a carbocation here. And now bromine will add on here to give us a product where both the bromine atoms are on the third carbon atom, right? Or we can get another product where the proton adds on here. Now if you look at these two, this is a secondary carbocation and this is a primary carbocation. That is the reason, because secondary carbocation is more stable, the proton attacks this carbon and we get a secondary carbocation here where the bromine can now attack Br minus to give us this. And further another molecule of HBr will attack. First protonation will take place. CH3, C, Br, CH3. In this protonation, again, there is a choice. Either protonation can take place on this carbon or this carbon. If it takes place on this carbon, we get a 2 degree cation here, 2 degree carbocation. If it takes place on the other carbon, we will get a 1 degree carbocation. CH3. Right? This is a 1 degree carbocation, this is a 2 degree carbocation, this is more stable. Hence, now Br will attack here and the final product will be Br here, another Br here and CH3, a geminal dihalide. So it is a Markovnikov's addition and the bromine will get attached to the carbon which has less number of hydrogens, and this is the addition of hydrogen halides which follows Markovnikov's rule and a carbocation mechanism. The next reaction is addition of water. Addition of water. Now we have said that alkynes are insoluble in water, so they don't react with water. But what happens in the presence of dilute sulfuric acid and mercuric sulfide at 333 Kelvin? Here ethyne reacts with water, HOH, Ag2 plus, 333 Kelvin, H plus, dilute sulfuric acid and mercuric sulfate. The negative part of the addendum again attaches itself to the carbon which has less number of hydrogens here. First we will get a vinylic alcohol. This vinylic alcohol isomerizes to give us ethanol. So we will get a carbonyl compound when water adds on to an alkyne. If we have another one, let's say propine, it adds on water in the presence of mercuric sulfate, Ag2 plus, H plus, 333 Kelvin, OH will get attached to the carbon having less number of hydrogens because it's a Marconi of addition. The mechanism is the same as we have discussed earlier. So we will get H3C OH double bond CH2. This is a vinylic alcohol which will isomerize to give us acetone, which is a ketone or a carbonyl compound. So addition of water results in the formation of carbonyl compounds. The last reaction is polymerization reaction. Polymerization. This addition reaction can be either a linear polymerization or a cyclic polymerization. In linear polymerization, if we have ethyne, it will polymerize under required condition of temperature and pressure and suitable catalyst if required to form these units. One, two, three, four, 1, 2, 3, 4, and these units, this monomer will be repeated to give us this polymer, which is called polyethylene or polyacetylene. This is a very important polymer, and under suitable conditions, it also conducts electricity. So it is used in electrodes in batteries also. The more important reaction, which is cyclic polymerization, is the reaction of an alkyne when it is passed through a hot iron tube at 873 or 600 degrees Celsius. We get ethyne will give us benzene. How does this happen? 873 Kelvin, red hot iron tube. If ethyne is passed through a red hot iron tube, 3 molecules of ethyne will polymerize. This can be drawn like this. H, H, C, H, H. This one goes here, this one goes here, this one goes here. This will undergo polymerization. These 3 molecules add together to give us benzene. Now, homologues of acetylene or ethyne also give this reaction. So, if we have a propyne, what will happen? 3 molecules of propyne will give us this product, a trimethyl benzene. So, this will be a 1, 3, 5 trimethyl benzene. Or if we have a butane, three molecules of this under these same conditions will give us a hexamethyl product, CH3, CH. This is hexamethyl benzene. So this is a very important reaction where an aliphatic compound gets converted to an aromatic compound. So these are the reactions for all the alkynes. They are electrophilic addition reactions and we have discussed them all. This is it for today. For today we discussed, just look here. We spoke about alkynes, their structure, nomenclature, their isomerism, physical properties, the acidic nature of alkynes, which is different from those of alkenes and alkenes, their methods of preparation and their chemical reactions. That's it for today. If you have any doubts, you can just write down your questions in the comment section and we will put up a video on Instagram or Facebook and we'll answer your doubts. Thank you so much for watching.